Diamagnetic materials create an induced magnetic field in a direction opposite to an externally applied magnetic field and are repelled by the applied magnetic field. In contrast, the opposite behavior is exhibited by paramagnetic materials. Diamagnetism is a quantum mechanical effect that occurs in all materials. When it is the only contribution to the magnetism, the material is called a diamagnet. Unlike a ferromagnet, a diamagnet is not a permanent magnet. Its magnetic permeability is less than mu naught, that is, the permeability of vacuum. In most materials, diamagnetism is a weak effect, but a superconductor repels the magnetic field entirely, apart from a thin layer at the surface. Diamagnets were first discovered in 1778 when Sebald Justinus Brugmans observed that bismuth and antimony were repelled by magnetic fields. In 1845, Michael Faraday demonstrated that it was a property of matter and concluded that every material responded to an applied magnetic field. He adopted the term diamagnetism after it was suggested to him by William Whewell. Diamagnetism, to a greater or lesser degree, is a property of all materials and always make a weak contribution to the material's response to a magnetic field. For materials that show some other form of magnetism, the diamagnetic contribution becomes negligible. Substances that mostly display diamagnetic behavior are termed diamagnetic materials or diamagnets. Materials called diamagnetic are those that laymen generally think of as non-magnetic and include water, wood, most organic materials such as petroleum, and some plastics and many metals including copper, particularly the heavy ones with many core electrons such as mercury, gold and bismuth. All conductors exhibit an effective diamagnetism when they experience a changing magnetic field. The Lorentz force on electrons causes them to circulate around, forming eddy currents. The eddy currents then produce an induced magnetic field opposite to the applied magnetic field, resisting the conductor's motion. After studying this module, you shall be able to know about the phenomena of diamagnetism, learn the classical and quantum mechanical theory of diamagnetism, identify the Pascal's constant and constitutive corrections, evaluate diamagnetic correction for some common ligands. Introduction to diamagnetism. Diamagnetism is the phenomena of a magnetic field inducing in a material a magnetic field which opposes it. In other words, a diamagnetic material has a negative magnetic susceptibility. The diamagnetic susceptibilities are very small in magnitude compared to the paramagnetic material and negligible compared to the ferromagnetic materials. The universally accepted explanation of diamagnetism is the precession of the magnetic moment created by the orbital motion of electrons. Diamagnetism can be explained by classical theory of diamagnetism and quantum mechanical theory of diamagnetism. Classical theory of diamagnetism. Diamagnetic substance has no permanent magnetic dipoles. Therefore, when a magnetic field is applied to it, no interaction tending to bring about an alignment of the magnetic dipoles with the field takes place. However, the substance experiences repulsion from the applied magnetic field. The flux density in diamagnetic substances is less than the flux density in the surrounding magnetic field, and the susceptibility is independent of temperature. The classical theory of diamagnetism can be explained using Langevin's theory. Let us consider an electron moving about the nucleus in an orbit. When this moving electron is subjected to an external magnetic field, the electron continues to move in an orbit, but the orbit as a whole precedes about the direction of the external magnetic field. In essence, the orbit normal describes a cone of radius r1, while the radius of the orbit is r. An electron of mass m moving in a closed orbit is equivalent to a current in a wire. The magnitude of this equivalent current is E by C into omega by 2 pi electromagnetic units, where E is the electronic charge, C is the velocity of light, and omega is the angular velocity of the electron. Such a current will produce a magnetic field of the same intensity at a given distance as a magnet of moment mu, such that mu is equals to E omega s upon 2 pi c is equals to E omega pi r1 square upon 2 pi c is equals to E omega r1 square upon 2c, where S is the area of the bounded surface around which the electron moves and r1 is the radius of the orbit. According to the Lenz's law, the direction of this induced magnetic field is opposite to that of the applied field. This effect is therefore expressed with a negative sign. It should be noted that the precessional velocity becomes zero when h is 0. If the orbit is not circular, omega r1 square may be replaced by an average, so that mu is equals to average E omega r1 square upon 2c. It has been shown by Larmor that imposition of a perpendicular external field H on such a system superposes on the electronic motion and angular velocity of precession given by L is equals to minus EH upon 2mc. The magnetic moment associated with the orbit will therefore be changed by delta mu is equals to E omega plus 1 r1 square by 2c minus E omega r1 square upon 2c. Therefore, delta mu is equals to El r1 square upon 2c. For a multi-electron atom, a system of n orbits oriented at random to the fields r1 square, the mean square radius of the projected orbit perpendicular to h becomes r1 square is equals to 2 upon 3 r square, where r square is the mean square radius of the orbit. The change of magnetic moment for atom will therefore be delta mu A is equals to E square H upon 6 mc square summation over m r square. The change of magnetic moment per gram atom will therefore be delta mu A is equals to minus n E square H upon 6 mc square summation over n r square, where n is the Avogadro's number. The susceptibility per gram atom is then chi A is equals to delta mu A upon H is equals to minus n E square upon 6 mc square summation r square is equals to minus 2.832 summation r square into 10 raised to power 10. A similar relation holds true for the spinning electron and spinning nucleus. The electron spin and nuclear spin hardly affect the diamagnetism of the orbiting electron because the nucleus has a mass much greater than that of the electron. The spinning electron has too much too small radius, that is approximately 10 raised to power minus 13 centimeter, as compared to the radius of the orbit, that is approximately 10 raised to power minus 8 centimeter. Quantum mechanical theory of diamagnetism. The quantum mechanical theory of magnetic susceptibilities has been treated by Van Vleck. The most interesting result is that the expression for diamagnetic susceptibilities is exactly the same as that already given in the classical theory. For instance, the atomic diamagnetic susceptibility of hydrogen may be calculated directly from the expression chi A is equals to minus 2.832 into 10 raised to power 10 into h square upon 4 pi square z e square m into 5 by 2 n raised to power 4 minus 3 by 2 n square l plus 1 plus half n square is equals to minus 0.79 into 10 raised to power minus 6 into 5 n raised to power 4 minus 3 n raised to power 2 l plus 1 plus n square upon 2z square, where n and l are the principal and subordinate quantum numbers respectively, and z is the atomic number. The quantity h is Planck's constant and m is the electron mass. For atomic hydrogen, n is equals to 1, l is equals to 0 and z is equals to 1. Hence the gram atomic susceptibility is equals to minus 2.37 into 10 raised to power minus 6. Unfortunately, there is no direct method of measuring the magnetic susceptibility of atomic hydrogen. Furthermore, atomic hydrogen is highly paramagnetic and diamagnetism would be concealed. An indirect method using Pascal's constant for combined hydrogen gives a value of 2.93 into 10 raised to power minus 6, which is about as good agreement as could be expected. Somewhat similar types of calculations have been made for helium and heavier atoms. There are some important points about diamagnetic susceptibility. First is it is negative. It explains it opposes the applied magnetic field. Second, it is an inherent property of a substance containing paired or unpaired electrons. However, it can be usually detected in a compound containing paired electrons, the unpaired electrons being paramagnetic overshadow diamagnetism. Third, diamagnetism depends only on the radius of the electron orbit. Fourth, it is independent of temperature. A slight variation in diamagnetic susceptibility with the change in temperature has to be reviewed in the light of expansion or contraction in the electron orbit. Fifth, diamagnetism is an induced effect and exists as long as H lasts. Pascal's constants and constitutive corrections. Although the classical theory susceptibility per gram atom equation gives an idea of diamagnetic susceptibility, in practice this is of little value because of uncertainty involved in evaluating the electron orbit radius. From measurement on a very large number of compounds, Pascal concluded that the susceptibilities could be represented by the expression chi m is equals to summation Na chi a plus summation lambda, where Na is the number of atoms of susceptibility chi a in the molecule and lambda is a constitutive correction depending on the nature of the bonds between the atoms. In this expression, chi a is not the theoretical atomic susceptibility but is a purely empirical constant derived from the measured susceptibility. We take an example from Pascal's work to show how he found out the value of chi c. We take an example from aliphatic series. For hexane, the value of chi m is equals to 79.6 into 10 raised to power minus 6. And for octane, the value is 103.7 into 10 raised to power minus 6. So the difference between the two is equals to 2 into 12.05 into 10 raised to power minus 6. For decane, the chi-m value is 129.7 into 10 raised to power minus 6, and the difference between octane and decane is 2 into 13.0 into 10 raised to power minus 6. From these data, the mean value of chi CH2 is minus 12.35 into 10 raised to power minus 6. Then chi C is equals to chi CH2 minus chi H, which is equals to minus 12.35 minus 2 into 3.05 into 10 raised to power minus 6. So chi C becomes minus 6.25 into 10 raised to power minus 6 CGS units. The value of chi H was obtained independently from measurements on hydrogen. Pascal's constant for some atoms, ions, species are given here. For H, chi dia is equals to minus 2.93, carbon minus 6, nitrogen in open chain it is minus 5.57, for nitrogen in ring minus 4.61, for nitrogen monoamide minus 1.54, nitrogen diamide or imide minus 2.11, oxygen In alcohol or ether, chi-dia is equals to minus 4.61. For oxygen in aldehyde or ketone, it is plus 1.73. For oxygen carboxylate, it is minus 7.95. For fluorine, minus 6.3. Chlorine, minus 20.1. Bromine, minus 30.6. Iodine, minus 44.6. Sulfur, minus 15. Phosphorus, minus 26.3. Silicon, minus 20. Thus, in the compounds containing the carbon double bond, he observed that the molar diamagnetic susceptibility values based on atom constants has to be corrected by plus 5.5 into 10 raised to power minus 6 CGS units to get a good fit with the experimental values. Similarly, the compounds containing the C triple bond has to be corrected by plus 0.8 into 10 raised to power minus 6 CGS units. Diamagnetic correction for some common ligands. The calculation of chi-m for some common ligands is as for acetate atom corrections. For 2 carbon, the atom correction is equals to minus 12.0 into 10 raised to power minus 6. For 3 hydrogen, it is minus 8.79 into 10 raised to power minus 6. For 2 oxygen in carboxylate, it is equals to minus 7.95 into 10 raised to power minus 6. Constitutive correction is summation lambda is equals to 0. So the atomic correction summation Na chi A is equals to minus 28.74 into 10 raised to power minus 6 CGS units compared to experimental value of minus 30 into 10 raised to power minus 6 CGS units. For pyridine, there are 5 carbon, so atom correction is equals to minus 30 into 10 raised to power minus 6. For 5 hydrogen, atom correction is equals to minus 14.65 into 10 raised to power minus 6. And nitrogen in ring is equals to minus 4.61 into 10 raised to power minus 6. There will be constitutive correction for 5 ring carbons, that is summation lambda is equals to minus 1.20 into 10 raised to power minus 6. So in total, atom correction plus constitutive correction becomes minus 49.26 into 10 raised to power minus 6 minus 1.20 into 10 raised to power minus 6. That becomes equals to minus 50.5 into 10 raised to power minus 6 CGS units compared to experimental value of minus 49 into 10 raised to power minus 6 CGS units. Another example is acetone, where there are 3 carbons. The atom corrections for 3 carbon is equals to minus 18 into 10 raised to power minus 6. For 6 hydrogen, it is minus 17.6 into 10 raised to power minus 6. And 1 oxygen in ketone is equals to 1.73 into 10 raised to power minus 6. In total, the atomic correction becomes minus 33.82 into 10 raised to power minus 6. And there is no any constitutive correction. So, chi-m is equals to minus 33.82 into 10 raised to power minus 6 as compared to the experimental value of minus 33.8 into 10 raised to power minus 6 CGS unit. There is another example, that is phenanthroline, where there are 12 carbons. For 12 carbons, the atom correction is equals to minus 72.00 into 10 raised to power minus 6. For 8 hydrogen, the atom correction is minus 23.44 into 10 raised to power minus 6, and for 2 ring nitrogens, the atom correction becomes minus 9.22 into 10 raised to power minus 6. In total, the atom correction is equals to minus 104.66 into 10 raised to power minus 6, and there will be constitutive correction in phenanthroline for 4 ring carbons and 4 binuclear carbons, and that is minus 1.9 into 10 raised to power minus 6 minus 12.3 into 10 raised to power minus 6, that becomes minus 14.2 into 10 raised to power minus 6. So chi m becomes minus 118.9 into 10 raised to power minus 6 compared to experimental value of minus 128 into 10 raised to power minus 6 CGS units. In text we have discussed the example of NN prime ethylene bis salicylene diamine 2,2 prime dipyridyl ethyl benzoyl acetate, etc. For a transition metal complex, one can measure only the net magnetism chi measured, which is the sum of paramagnetic chi para and diamagnetic chi dia contribution. So chi para is equals to chi measured minus chi dia. Thus, to obtain the paramagnetic susceptibility, the diamagnetic susceptibility must be subtracted from the net susceptibility. This can be achieved by first by using the values of Pascal's constant reported in table to estimate chi dia. Second, by measuring the diamagnetic susceptibility of the ligand and adding that of the metal from table to obtain chi dia. Third, by making an analogous diamagnetic metal complex and using its value as an estimate of chi dia. Summary. In this module, we have discussed the classical theory of diamagnetism and quantum mechanical theory of diamagnetism. These theories of diamagnetism lead to some important points about diamagnetic susceptibility. First, it is negative. It is an inherent property of a substance containing paired or unpaired electron. And third, diamagnetism depends only on the radius of electronic orbits. 4. It is independent of temperature. 5th, diamagnetism is an induced effect and exists as long as H lasts. A method derived by Pascal to find out diamagnetic susceptibility of various atoms, ions, or species. Pascal's method is based on the experimental susceptibility of some atoms. Diamagnetic correction for some common ligands using Pascal's method. The experimental net magnetism chi measured is the sum of the paramagnetic chi para and diamagnetic chi dia contributions. So, chi para is equals to chi measured minus chi dia.